So today we talk about cement chemistry. So our lecture number 2. Okay. So we'll learn first of all what are different type of cement from historical cement, and what is non-hydraulic cement, and what is hydraulic cement. Okay. We also discuss the manufacturing process of cement, and also the major chemicals and the major compound in cement. For the next class, we will discuss the 5 major different type of cement and what is the hydration process. Hydration, by the way, is the chemical reaction between cement and water, and also the strength of cement. Before we start, let's look at the ancient cement. 5,000 years ago, ancient Egyptians, they use gypsum. Okay, so first of all, we heat up the gypsum, calcium sulfate with 2 parts of water to 130 degrees Celsius. So the gypsum will decompose into calcium sulfate hydrate plus water. Okay. And then they will ground this calcium sulfate hydrate into powder form and mix with water again, which is the second chemical reaction here, and then it will form gypsum again. Okay. Ancient Roman engineers use so-called lime mortar. So first of all, they heat up this CeEC3, which is limestone, calcium carbonate, to 1,000 degrees Celsius. So as you can see, much higher degree than what the ancient Egyptians do. Okay. Then the limestone will decompose into calcium oxide, CaO, plus carbon dioxide. Okay. And CaO is also called lime. We then grind this lime into powder form and mix with water, the second equation here, and then we get CaOH2, which is calcium hydroxide. Okay. The calcium hydroxide will react with CO2 from the air, harden again. And we can see it become calcium carbonate limestone again. So calcium carbonate is very strong under compression. In the process, water will evaporate. Okay, so ancient Egyptians using gypsum and ancient Roman engineers using limestone as their so-called concrete. Okay. As we will see, the modern concrete are totally different from what they used 1,000 years ago. The so-called non-hydraulic cement, including what we just discussed, the product is formed by carbonation, but the final product is not resistant to water. Okay. Why we say that? Let me show you the chemical reaction. For example, the gypsum can be dissolved into water. Limestone seems to resist to water, but actually it is not. Let me write down the new equation here. Okay. So limestone is CaCO3. Okay. It can actually react with carbon dioxide from the air plus 1 part of water. Okay. And we'll get a new product. Okay. So this is called calcium bicarbonate. Okay. And this is actually can be dissolved in water. So limestone, CaCO3 is not totally resistant to water. Okay. So the concrete ancient Roman engineering used is not water-resistant concrete, so it's non-hydraulic cement. But sometimes when we add materials, so-called pozzolands, such as volcanic ash, so the major chemical in pozzolands is silica oxide. So silica oxide plus lime, CaO, plus water, it can form a new material called CSH. Okay. So CSH actually is a major component in modern cement, and the strength of CSH is very strong. Okay, so this is non-hydraulic cement. Hydraulic cement, by definition, is hardened by reacting with water and form a water-resistant cement, concrete product. For example, CSH. Modern cement is called Portland cement. Is one example of hydraulic cement. Okay. Right, and this slide is showing us the history more of modern cement. The first natural hydraulic cement is coming from England, 1796, by calcinating nodules of impure limestone containing clay. The major component for cement is limestone, CaCO3, and also clay. So inside clay, we have silica oxide, we have aluminum oxide. Okay. 1813, French chemist Vicat produced artificial hydraulic lime with mix of also limestone and clay. And the word Portland cement we use today is first patented by Joseph Aspling in England. Okay. The reason we call that Portland cement is not because the source of cement is coming from Portland. It's just because the color of the stone of modern cement is similar to the color of the stone from Portland, which is a small isle in England. As we can see from here, we have two samples. The quarry stone, which is on the left, has gray color, and on the right is a modern concrete. So the color of these two materials are almost the same, and that's the reason why we call that Portland cement. Okay, just a name. Okay, and the manufacturing process of cement, including first of all, we need to get the raw materials. The raw materials can be getting from natural resource, such as limestone and clay, or industry byproducts, such as silica fume, coal ash, or slag. Okay. But remember, the major four component raw materials are lime, iron, silica, and aluminum. Okay. So if we get the first letter for all these every words, we get LISA or Lisa. Okay. So remember Lisa, so that's the four major raw materials we needed to produce modern cement. Okay. And then the next step is we need to prepare the raw materials, proportion different type of materials, and ground them. Okay. Before we burn these raw materials in a big oven, we call that clinkering process. Okay. And finally, we get clinker, and we need to grind the clinker into a fine powder. Okay. Where we get cement. Right. The source of cement, okay, for calcium, we can get from natural resource such as limestone, or we can get from industry byproduct such as cement kiln dust. So this is the waste materials all coming from slag. Slag is byproduct of steel producing process. Okay. For iron, we can get that from clay or iron ore or some other sources. For silicon, the major source are clay, which is natural source, or flash or slag. Okay. Flash is also called coal ash. So this is a byproduct of the coal burning process. Here in the state of Hawaii, every year we generate around 300,000 tons of flash locally. Okay. And most of these are not used. Okay. For alumina, we can get that from clay, from flash or slag, and other sources. The fifth component is sulfate, okay? Mainly coming from gypsum. The reason we add sulfate into clinker to form a cement is to control the setting time. Without the sulfate, the chemical reaction between clinker and water will be too fast. Okay? So when you mix cement with water, we need enough time, typically around 2 to 4 hours before the cement hardens. So we can have enough time to mix it, transport it, cast it, and finish it. Okay? So we add gypsum to control the setting time, slow down the chemical reaction. There's some other minor functions for gypsum, such as reduce the shrinkage and also improve the strength development of concrete. The major function of sulfate is to increase the setting time. We'll talk about that in much more details. All right, and here is the PCA video. PCA is Portland Cement Association, I think in Illinois, about cement production.
Portland cements are manufactured by a process that begins by combining a source of lime, such as limestone, with silica and alumina, usually from clay, and a source of iron oxide, such as iron ore. The selected raw materials are then crushed, blended, and burned in a kiln to produce clinker. Once cooled, the clinker, with a small amount of gypsum added to regulate the setting time of the cement, is ground in a mill to produce the extremely fine-grained powder called Portland cement.
Okay, again, the first step is to get the raw materials. The stones, limestone, clay is first reduced to a smaller size, okay, so around less than 1 inch, and stored. Okay. And then these raw materials need to be grounded into powder form and blended based on the design proportion. Okay, so limestone, sand, clay, iron ore need to be proportioned based on the design. Okay. To ground the raw materials, we could use a so-called dry process where no water is added during the grinding process, or wet process where water is added during the grinding process. Dry process is currently used by modern cement producer, okay, because the energy use will be less for the dry process. Okay. So again, dry process is more used in modern days. Okay. So after grinding, the raw materials will be stored. Right. So the third step is to burn the raw materials. We put the raw materials into a big oven, okay, which is slowly rotated, and there's a small slope. So the raw materials fit to the higher end, and the big oven is slowly rotated. Okay. So materials will slowly go from the higher end to the lower end, the temperature in the different section of the kiln is also different. So during this burning process, different compound will be produced. Okay, so finally we get the clinker. Materials are also stored separately. Gypsum here is added again to slow down the chemical reaction to control the setting time of concrete. And the final step, so clinker together with gypsum is grounded into fine powder form. So we have Portland cement. Okay, so that's the cement we see. We can buy from Home Depot, Lowe's in bags. Okay. So here shows some picture of the raw materials. This is the limestone and clay, the quarry. This is the crushing process. So blend different type of raw materials into different proportion. As we can see, the raw materials is already grounded into fine powder. And here's the overview of the power plant. We have, first of all, raw materials blending and storage here. And then the raw materials will be further grounded before going to the oven. We call that kiln. Okay. So kiln is slowly rotate. At the lower end of the kiln, we have clinker formed. Okay. This is clinker storage. Okay. So clinker will be grounded together with gypsum. So we have cement. This is cement grinding. Okay. And here shows a picture of kiln, the big oven. So one thing I want to mention about cement production is it is a very high energy intensive process. In the process, also a lot of greenhouse gases such as carbon dioxide is generated. So actually for every 10 of cement produced, it will generate 1/10 of carbon dioxide. So a lot of greenhouse gases is produced during the process. Also, a lot of energy is used during the burning process. Okay, it is estimated that around 5 to 10% of total man-made greenhouse gases is generated because of cement production. Okay, so one of the major research focus for cement researchers is to produce sustainable cement or materials which can replace cement, so we can reduce energy consumed and also increase the sustainability of concrete. Okay, we'll talk about that in future lectures. Okay. All right, again, here shows schematic process of cement production. First of all, we need to get raw materials such as limestone, clay, and shale. So we have the 4 major components: calcium, iron, aluminum, and silica. Okay, so also called LiSa or Lisa. So we're grinding these raw materials, preheat before going to the burning process in the kiln. Okay. And don't forget to add gypsum to control the setting time. And then when we get a clinker, it will be finally grounded with gypsum. So we have Portland cement. So take a closer view of the what happened in the kiln. Okay. So the raw material is feeded on the higher end. Okay, based on the temperature, here is the temperature of the gas. Here's the temperature of the raw materials or the feed. Okay, so we have dehydration zone, which is water will be evaporated. Okay, and also some of the clay will decompose and release the water, release the CO2. Okay. The second zone is called calcination zone, where the raw materials will be further decomposed and release CO2 and other gases. So limestone will decompose here, and we have some initial formation of compounds. Okay. The compound in this lecture is the major product which will react with water. Okay. So that's a five different type of compound which we'll discuss in a moment, such as C2S. Okay, C2S is one of the major compound. Okay. And also in the clinkering zone, we have formation of melt, which is actually a mixture of another two type of compound, C3A and C4AF. Okay. And C3S is another major compound. Okay. And then we have the cooling zone, so the clinker will be out from the lower end of the cube. And here is a picture of the clinker. Looks like charcoal. The size is around 3/4 inch to 1 inch. Okay. And the gypsum is the whitish color. Gypsum together with clinker is finally grounded into Portland cement. So again, what is the function of gypsum? So we add gypsum to control the setting time, to slow down the chemical reaction between the clinker and water. Okay. All right, so when we get cement, we need to deliver cement and also storage cement. Okay. So here's a video about delivery.
Portland cement is available as a bulk powder or in waterproof bags. Most Portland cements are shipped in bulk using closed tanker trucks, covered rail hopper cars, rail tank cars, covered barges or ships with closed compartments. Pneumatic loading and unloading of the transport vehicle is the most popular means of handling bulk cement.
Right. Storage of cement.
Portland cement is a moisture-sensitive material. If kept dry, it will retain its quality indefinitely. Cement stored in contact with damp air or moisture sets more slowly and has less strength than Portland cement that has been kept dry. The relative humidity in a warehouse or shed used to store bagged cement should be as low as possible. Cement bags should not be stored on damp floors but should rest on pallets. Bags should be stacked close together to reduce air circulation, but should never be stacked against outside walls. Where a shed is not available, bags should be placed on raised wooden platforms at least 4 to 6 inches above the ground. Waterproof coverings should fit over the pile and extend over the edges of the platform to prevent rain from reaching the cement and platform.
Okay, so cement powder is very sensitive to moisture. So we need to keep it 100% dry before we use it. Okay, so otherwise the fine particles of cement will stick together. The typical size of cement particle is around 10 micrometer, 10 to 20 micrometer. So when we have moisture in cement, the fine powder will stick together, so it will reduce the efficiency of cement. So keep it dry during the storage. Okay, so this slide is very important together with the next one. Okay, so here shows the typical chemical composition, or we call that constituent materials of cement. Okay. So again, we have 4 major oxides: lime, silica, alumina, and ferric oxide. Okay. So lime is calcium oxide, CaO. In cement chemistry, we use a shorthand C to represent CaO. Okay. The reason for that is if you read everything in details, the equation will be too long. Okay. So we use shorthand in cement chemistry. So C is a shorthand for calcium oxide, CaO. It is not carbon atom. Okay. So similarly, for silica oxide, SiO2, the shorthand is S. Okay. So S here is not sulfur atom. It is shorthand for silica oxide. Okay. Aluminum oxide, Al2O3, the shorthand is A. And ferric oxide, Fe2O3, the shorthand is F. So these 4 major components take more than 90% of the total weight of oxide in cement. Okay, especially calcium oxide. So more than 50% in typical Portland cement. There's some minor oxides such as magnesium oxide. The shorthand is M. And also some carbon dioxide, CaO. Look at the shorthand is C with a dash line on top. Okay, so this is the shorthand for CO2. So we can see the difference between C without dash line on top is for calcium oxide. C with a dash line on top is for CO2. For water, the shorthand is H. Okay, H is not for hydrogen atom, is for water, H2O. And S with dash line on top is for sulfur trioxide. So you can see the difference between sulfur trioxide versus silica. S without dash line on top is for silica. Okay. Right. So these are the shorthand we need to remember for cement chemistry. Again, please spend some time to remember this. This is important slides. And based on that, we have the typical cement composition or compound. Okay, so compound, as we can see, is combination of 2 or more type of oxide we discussed earlier.
Oh.
The most important compound is tricalcium silicate. Okay, the formula is 3 parts of calcium oxide with 1 part of silica oxide. Okay, the shorthand here is C3S. Okay, we see the C3S symbol from the cement production in what happened in the cube. So C3S here is for tricalcium silicate, 3 parts of calcium oxide and 1 part of silica oxide. So take about 50% plus or minus for modern Portland cement, depending on the type of cement. Okay, so we'll discuss in more details next time. The second compound is called C2S. The full name is called dicalcium silicate. Okay, we have 2 parts of calcium oxide and 1 part of silica oxide. Okay, there's another name, A-light for C3S and B-light for C2S. Okay. A-light actually is the mineral with C3S together with some of the minor chemicals. Okay. So B-light is actually C2S with some minor impurities, some other small amount of chemicals. The third one is C3A. The full name is tricalcium aluminate. So 3 parts of calcium oxide with 1 part of aluminum oxide. The fourth one is C4AF. It's called tetracalcium aluminum ferrite. So tetra is for 4, so 4 part of calcium oxide with every part of aluminum oxide and ferric oxide. Okay. And the 5th compound, the gypsum, is CaSO4 with 2 parts of water. Okay, the shorthand is this. Okay. Depending on type of cement, the amount of gypsum is around 2 to 5%. Again, here Elite is C3S with some impurities, such as magnesium oxide. Right. So please spend some time to remember the shorthand. Okay. So in the future lectures, mostly we'll talk about the shorthand, such as what happened between C3S and water. Okay. All right. Lastly, let's talk about quality control of cement. So when we produce a cement clinker, we want to know the percentage of these different compounds, how much C2S we have, how much C3S we have, and how much C3A and C4AF we have. That's several different methods we can use. Photomicrograph is one of the methods. So first of all, we get sample of clinker, and we cut the surface, to polish the clinker surface. And then we take a picture of that, and based on the morphology, basically what the color, shape of different compound, we can count how many pistons in each of the compound. And based on that, we can roughly estimate what the percentage of mass for different compound. Okay. For example, C2S has dark color and round shape. On the other hand, C3S has light color but angular shape. Everything in between is a mixture of C3A and C4AF. Okay. So actually, we cannot tell the difference between C3A and C4AF based on photomicrograph. Okay. Right. So this is the actual picture using scanning electron microscope for clinker. Okay. So B-like C2S is the darker rounded crystals like this, and this C3S is light color with angular shape. Okay. Again, everything in between is a mixture of C3A and C4AF. Right. The picture on the right showing us scanning electron microscope of A-light. Okay. So this is the angular shape crystals. Probably you have heard about XRD or X-ray diffraction. This is another method we can use to quantify how much different compound in a clinker sample. Okay. The basics of XRD is not the focus of this class. I offer another graduate level class called Advanced Concrete Technology, CEE375, which will discuss more details about different type of microstructure analysis and chemical analysis for cement, concrete, and other type of construction materials. But here in this class, we only need to know we can use XRD to tell what type of crystals in a sample, and also roughly what are the percentage for each type of crystals, such as C2S and C3S. Okay. So every type of crystals, such as C3S, they have a certain shape of the curve. Okay. Something like fingerprint for every person. So they have a signature shape for the XRD curve. So based on that, we know what type of crystals and also what are the percentage for each type of crystals. Okay. So that's the XRD we can use to do the quality control for cement clinker. Right. So here is another picture of XRD. A is for A light or C3S. B is for B light or C2S. Okay. Some of the peaks for A light and B light are overlap, so make it pretty complicated to tell what are the percentage for each compound. Right. Here shows a picture of Portland cement. Normal Portland cement has this grayish color, so gray color. If we using scanning electron microscope, the scale here is around 50 micrometer. Okay, we can see cement particle is angular shape. The average size of cement particles it is around 10 to 20 micrometer. Okay. Right. So this is a short introduction of what is Portland cement, what are the manufacturing process of Portland cement, and also what are the major oxide and major compound in cement. Okay. Keep this question in mind. What are the raw materials we use to produce cement? Remember one word, Lisa. Okay. Why cement need to be kept dry? Okay. If we mix water with cement, it will have reaction. We'll talk about this reaction in lecture number 3 next time. What are the major oxide in cement? Okay, calcium oxide, silica oxide, aluminum oxide, and ferric oxide, together with some sulfate oxide to produce gypsum. And what are the major compound in cement? Okay, C3S, C2S, C3A, C4AF, plus the gypsum. So these are the 5 major compounds in Portland cement. All right, so reading suggestions, and that's the end for this lecture. Any questions before we dismiss?
For the cement quality control and the X-ray diffraction,
yes.
Why do we need to do those things if we've mixed the concrete? Shouldn't we know what's in it already?
It is very good questions. It is because, as we discussed in lecture number 3 next week, different compound will react different with water. Okay, for example, C3S will react much faster compared to C2S, although the hydration product of these two will be similar. On the other hand, C3S will react super fast with water, and the hydration product is totally different. Okay, so we have to know what are the percentage of these 5 major compounds, so we can predict what will be the end product. Okay, so we need to know the percentage for each compound before we use it. Yeah, good questions. Any other questions? All right, thank you so much. I will see you Monday next week at 8:30. Thank you. If you have questions, you can stay here and ask. Thank you.
Thank you.
Thank you.